Sorry, I was muted. Everyone can see my screen?
Yes.
Awesome, thank you. So, today we're going to create a more fun validator, and one that is actually useful in several different cases. So imagine that you want to give some money to your grandson or some person that is some child of your family. So you want to make sure that that person gets the money eventually, but if you give your 13-year-old son money right now, he might like burn it in, I don't know, buying Pokemon cards or something like that. So you don't want to do that. You want to make sure that he's going to get the money, but once he's 18 or 21 or whatever age you think it's appropriate. So for that, there's a usual schema that is called vesting, that we can create one validator that checks. We want a validator everyone can see me. Yes. Okay, that's big enough, right? So we want a validator hold the ADA money, whatever, until a deadline, and after that only release it to a specific person. This is what we want to achieve. Let's open. No, didn't work like that. Perfect. So this is what we want to achieve. So think about it, like how we could do a smart contract that does that. We want to check only two things, really. We want to check if the deadline passed, and if the person unlocking, actually trying to unlock, oh, sorry. No, what did I just did? Oh my God, I closed. Oh, let's see. There you go. No? One second, and I just lost the drawing. 2024. There you go. So we want to check that the deadline passed, and if the person trying to unlock the ADA is a specific person. So we went from what we want, like what the end user wants, to specific checks that we can translate to the validator. So let's do just that. We called the validator, we call it vesting. So I just created a file. You can create this file in your, like, anywhere. It just needs to be inside validators. I just reordered a bit, so I created lesson 1. Lesson 1 has the validators that we used before. In lesson 2, we are going to see the vesting example, and then we're going to see how we can parameterize it. So, as always, what do we want? We want a validator. And this validator, we're going to call this validator vesting. So, the validator takes 3 parameters: the datum, the redeemer, and the script contents. So far, we ignored the datum in the smart contract itself. We only use the redeemer once when we check that the redeemer was equal to this hard-coded 42. And we never use script contents. Right now we have an error because we are getting this script context type from nowhere, so we have to import it. So we can use the LSP for that. That just adds it. So we have our empty validator. The validator. It's an expression, a block that contains inside, in this case, just one function called vesting that takes 3 parameters and returns a Boolean. And then comes the body of the function, which is empty so far. So the first thing we need to do pretty much every time is to check what is the purpose of the validator. We want to spend a UTXO, we want to mint, we want to stake. So we have all these possibilities, but in this case, we just want to consume a UTXO. And now I remember that close to the end of the lecture, someone asked what was if I could define UTXO. So we're going to do that really quickly, just so everybody is on the same page. Like UTXO is something that you have to have like an intuitive feel for it. So imagine that we have a bunch of we start using the Cardano blockchain, and because the Cardano blockchain has a history, like people did transactions previously, we have a bunch of things that are part of the blockchain. So we have these things, and these things contain value, contain information. These things come, like every one of them. Oh, we have a question?
Not.
No? Okay. So, yeah. Okay. So all these things come from somewhere. They come from prior transactions that we don't care about because we weren't part of the blockchain by then. We just care about the blockchain now. But if we go far enough, eventually we will find a single of these things that is the first of all that contain all the value, and then it started to spread. That's the Genesis block. So we have all these things, and these things come from somewhere. From where they come? From a transaction. All these things, as Lars has said previously, the only thing that Cardano does is to record inputs and outputs of transactions. So record transactions, basically. So there's nothing else besides transactions. So these are something that was produced by a transaction. Somewhere in the past did a transaction and outputted 1, 2, or maybe dozen of these things. The transaction outputted this to the blockchain, so these are transaction outputs. And then when we want to, like, each one of these are transaction outputs. Let's call it, let's put it like every single one of them is a transaction output. Then someone else wanted to use the money or the assets that were locked in this one or in this two from the bottom. So this person created a transaction. As you can see, this block represents a transaction. We use TX as a short for transaction. So this transaction consume or spend these outputs and generated, for example, one more output. Sorry. So these are all transaction outputs. I think it should. Everybody's on board until now. We have a bunch of transaction outputs. These ones are from prior transactions, and that actually we can do like a huge rectangle here, and there you go. We have this huge transaction 1 and transaction 2. So they are all outputs, but they are different because now when we are at this point in time after the second transaction, these two have been already consumed by this transaction, and that generated a different output. So there's a vital difference here. If we want to create a third transaction here, we cannot use this. This has already been spent. So we need to like differentiate these transactions, these outputs, to the ones that can't and cannot be spent. So that's why we call this output that has not been spent, and this one that has not been spent either, we call them unspent transaction outputs, which we use. These are the U for unspent, TX for transaction, and O for output. Use unspent transaction output. This is not an unspent transaction output. This is a spent transaction output. So we cannot use it. We don't care about this. This is just the history of the blockchain, not something we can interact with because it has already been spent. So we don't. These ones are not part of the these two are not UTXOs. These two are spent TXOs. So this one is as well an unspent transaction output because TX3 could either consume this one or this one, but cannot consume this one. So for the person that I don't recall who was it that asked if I could define UTXO, that's a UTXO, an unspent transaction output. So what we want to do with this validator is to consume a UTXO. So the purpose of the transaction is to spend. If we run the documentation, let's say Aiken docs, and we have a warning because we have a to-do right here that we're not, it's the compiler is letting us know that we're not finished. It's okay, we can run it anyways. And we serve the docs. Opening browser. Now, if we go to the standard library and to script context, as I said in the prior lesson, script context contains everything about the transaction that is not the datum and the redeemer, so everything else. And because we want to check if the transaction wants to consume an output, a UTXO, we need to check that information has to be inside the script context. So we go to script context. Script context contains a transaction and purpose. We care about the purpose. So script purpose characterizes the kind of the script being executed. So we can have minting policy, spend validators. We can script that withdraw rewards from staking and ones that deal with certificates. In our case, this we want to check if this is a spend validator, which is scripts that are used as payment credit for address in transaction output. So I think, yes, here is a better explanation. They govern the rule by which the output they reference can be spent. So this is what we want. We want to rule who can consume my UTX, my vesting UTXO. So to do that, we can use pattern matching. As you recall from Haskell, that's a really nice and useful way to branch out logic. And Aiken has pattern matching as well. It's a bit different, but it's still the concept is the same. So to pattern match in Aiken, we say when a specific value, in this case, is a value that is, as we saw prior, we have the script context, and inside we have purpose. So let's do that. Let's uncomment. Let's tell the compiler that we are going to use the script context. So when the context dot purpose, we say context, we are here, and we say that purpose because purpose is a value inside the script context. So purpose dot purpose, and now this value name purpose is of type script purpose. So it can be this script purpose type has these 4 constructors. So now we can pattern match for all these 4 constructors. So if the script purpose is, and then I open a block, an expression, everything that is inside square bracket, not square, squiggly brackets are expressions. So a validator is an expression, and whatever is inside the vesting function is an expression, and then whatever is inside this pattern matching is an expression as well. So when the context purpose is, and I say spend output reference. So I can say spend, and I can say here output out ref, for example, because I can name, I know that this is the value of a value of type output reference, but I can name it however I want. Actually, not only I can name it however I want, but I can ignore it using the same as we did here. We can just put an underscore, and now we are ignoring the output reference that we are consuming. This output reference is tells us what is the output, the UTXO that we are trying to consume with this script. In this case, we don't really care about the exact output reference. We just care about, like as we said before, who signs it and what's the deadline. So we just ignore it, and then we use the right arrow to continue our logic in the case that it's the context purpose matches the spend constructor. So here I can say to do, and here I should, as you recall from Haskell, like pattern match for the rest of the constructors, but as well as same as Haskell, I can choose to ignore them by purposefully matching for anything else. So we first check if it's the spend. If it's the spend, we'll see what we're going to do. But if it's not, someone is trying to use this validator for something that is not consuming a UTXO. So in that case, we want to fail. We want to fail because the only thing we care about is about consuming with this specific validator. If the person is trying to use this validator to mint something, it's going to fail. If he's trying to use it to withdraw something, it's going to fail. You can only use this validator if you're trying to consume a UTXO sitting at this validator's address. Here we're having an error because we haven't imported spend, so we import spend from Aiken/transaction. And here as well, oh, it's not fail, it's false. Remember that we are returning booleans. So we have to eventually, doesn't matter what we do inside the validator, we have to eventually return true or false. So in the case that we're not trying to spend, we just return false, which means that the transaction fails. So now we want to do something right here. So what happens if we spend the transaction? So we said two things right here. We said two things, which I'm not finding. Somewhere I put our requirement and it's gone. It's okay. So we said that we want, I'm going to put it right here. We want to check the correct person signed and that it's after the deadline. This is what we want to check. So let's do that. Let's first check if the correct person signed. Now we can check who signed the transaction because that information is inside the script context. But the thing is, we have no idea who should have signed it because that's something we have to choose. We have to choose who is the one that is able to unlock it. And for that, we cannot just put the name of the person here because that's not a valid identifier in a blockchain or in any system. So the way that we identify people, persons or entities in the blockchain is using the public key hash of the person. As when we create a wallet, as we saw in the prior lesson, we create a private key, and then we use that private key to sign a transaction and to sign stuff. And then someone else can verify that I signed the transaction using the public key hash. So that's what we're going to use to identify everyone. So if we come here and we're trying to search for public key hash, we won't find a specific, we will find this payment credential type, not the public key hash. But if these are credentials, we have payment credentials, we have general credentials in general. But if we take a look at this, we have this verification key credential and this script credential. Everything is a hash, is something that is of type hash using this Blake 2B 224 algorithm. So remember when Lars explained how key works, we said that everything is a hash. So we hash verifications key, we hash the script, we hash stuff, and then we can use that to verify. So there's no abstract value, abstract name that we use here. So we need the hash of type Blake 2B224, which is the one that we use in Cardano. Ethereum uses a different one, and other. Actually, now in Plutus V3 that is going to be out soon. We also have the same algorithm. We have multiple more algorithms. We still use Blake 2B224, but we also have access to the Ethereum one if needed. But this is what we use. So we hash this verification key, and this verification key what's this? It's just a byte array. So it's an array of bytes that we call verification key to make sure that when we try to manipulate it, we have a more specific type. We don't shoot ourselves in the foot. So this is what we need. So now we can here, for example, create a type. We can create a type using the type keyword type. This is how create a type. And we have to name the type. We're going to name investing datum, because we're going to pass this as a datum. And here we use these squiggly brackets, and now we have to write the constructors. So this is, I mean, for example, we could create the maybe type in Haskell. Everybody already knows what's the maybe type. So we can create the type maybe that contains the constructors nothing and just. And here we have to use this a, just a, and this maybe type is polymorphic on a, something like this. So this will be the maybe type. So we write the name of the type, the constructors, and the constructors can be nullary constructors, meaning they have no constructors, no values inside, or they can. So in our case, vesting datum, we just need a single constructor, and so we can just name it the same as the type, vesting datum. And vesting datum has to contain the beneficiary of my UTXO. I'm just leaving something and someone is going to profit from it. And I want that beneficiary to be a specific person. So the type of beneficiary, as we just saw right here, verification key, as we just saw right here, has to be a hash of Blake 2B224 verification key. So actually we can just copy and paste it if we want. So beneficiary, all this, the beneficiary is a hash of a verification key. And for now, this is all, this is everything we need. We are not getting any errors because I'm just trying to add here the to do. So there you go. So now we get the errors that we are not importing these ones, And now we have to import verification key. And now we have to import hash. And we are not using the constructor. We're going to use it. So now we have to use this constructor. We have to use this type. So we're going to pass it as datum. We're going to name it datum so it's more obvious. And instead of being a generic data, it's going to be a vesting datum. There you go. Now we're using the vesting datum, but we're not using the value datum, but we will eventually. So we have the beneficiary. Now we can check if whoever signed the transaction is this beneficiary or not. So let's do that. Now we need to know who signed the transaction. Let's see. Let's go to script context. Script context. And inside script context, we already checked the purpose. The purpose doesn't contain any more information that is useful for us. So we go to transaction. There you go, transaction. A Cardano transaction as seen by Plutus scripts. So we have this transaction has a single, the type transaction has a single constructor called transaction. So it's the same. And it has all these inputs. So prior we showed them, but we didn't really use them. Now we're going to use them. So we want to know who signed the transaction. And who signed the transaction is inside this extra signatories type. As you can see, this type is a list of the hashes of using Blake of verification keys. So this is a list of hashes of people that signed the transaction. Potentially multiple persons signed the transaction. So we have a list of these public key hashes. But we just want to know if this specific one was the one that is inside this list. So all we need to do now, let's open these squiggly brackets to have an expression. So let's see, we can say we use the let keyword to name a parameter, to name something. So people that signed. So where are these people? Well, as we saw just now, context dot transaction dot extra signatories. So we have this. We have an error because it's a block that is not returning an expression. This is not an expression. We are creating. We are naming something, but we are not returning an expression. So we have an error. It's okay. We will fix this. So, okay, we have all the people that signed, and inside the datum, we have the beneficiary. This is of type, let's see, doesn't say, but we have it right here. It's a list. So we have to deal with list now. How can we check if something is inside a list? So we can just say here, list, Aiken list, and we can explore. So we have any, adds, concats. I mean, all these should be familiar because they do the same as the counterparts in Haskell. Delete, difference, drop while, filter. Filter we could use. We could filter it, but I know that there's a simpler one. Find, flat map, fold right, fold left, fold right. They behave same as in Haskell, but they are strict because Bluetooth is strict. And we have this has one that is a really interesting one because it figures out whether a list contains a given element. So if we try to find it, we've had to find, and then, okay, let's extract it from there and check if that is equal to the other thing. Has already does everything from us. So we need to provide a list and an element. That's, as you can see, this is a list of type A. It has elements of type A, and we provide another element of type A, and it tells us if this element is inside this list. As you can see, list has of a list 1, 2, 3. Element 2 says that it's true. 2 is inside this list. So we're going to use that right now. So let's see. We can say list, because we need to access the list module dot has, and we can save so we can get the error, so we can import it. So list has, and now we get the error because we need the two values, and we have to provide first the list and then the element, so people that signed, and then now we have to provide the element. The element is datum that we get from the inputs of the validator, and the datum if of type vesting datum, so we can access the beneficiary right here, datum dot beneficiary. And if we save, there you go. We are checking that the list people that signed contains the datum dot beneficiary value, and if it does, it returns a Boolean, which is exactly what we need to return for any validator. Right here, we need
Can
to
I ask a question about Icon at this point, Robertino?
Sorry?
Sorry, I just have an Icon question at this point.
Yeah.
This has function. I mean, in Haskell, that would obviously need a type class constraint like eq constraint to work. And in Icon, I think there's no such thing as type class constraints, right?
Right. There's
But
not.
I mean, Icon also has first class functions, right? And normally you can't compare functions for equality. So what would happen if you use this has on a list of functions? I mean, does it give a runtime error, or what? How does that work? Do you have any idea?
No idea, but we could check actually.
That was a curiosity. I mean, maybe we can check later.
Yeah.
I was wondering how they fix that problem, because I mean, Haskell does that for a reason, of course, that it doesn't allow it for arbitrary lists.
Yeah.
Right. Sorry, I didn't.
No, good point. But we can check once we finish the validator. We can try it out like live and see what's going.
Yes, let's do that. Sorry, thank you.
No problem. So okay, so we checked if the beneficiary signed the transaction. And this is a valid validator. This is, I mean, we have something that works, but it doesn't take into account the date. Now, if I create a transaction, as explained before, to my 13-year-old son, he can instantly unlock the transaction because he has the correct key. So we also want to check that the deadline passed. Deadlines time, actually, in Cardano, it's very specific. Let's see. Let's draw a bit. So Lars said in a previous lesson that transactions are deterministic. And why are they deterministic? Well, because we have all the information available. The node has all the information related to that specific transaction, and we have it before submitting the transaction. So both ourselves and the node have the same information, and we can be sure of that. So that way, when we validate the transaction in our own wallets, in our own computers, and it passes, we can be reasonably sure that it's going to pass. So why reasonably sure and not completely sure? So let's see. There are two phases in a validation in Cardano. So there are a bunch of stuff that are cheap to compute. We can check if all the outputs needed are there. For example, this is just a simple query that any node and can do instantly because they already have in memory all the UTXOs to be, and all the.
Is
Let's
output the right word here? Shouldn't it be input? I mean, of course, it's yeah.
Yeah. Okay. There you go. Yes. So all the inputs that we want to consume, all the UTXOs that we want to consume are there. The one that we are going to generate, of course, are going to be there because they are going to be generated by us. We can also check that the types of provided values are okay. We can check a bunch of other things. The important thing is that it's there you go, cheap. It's cheap, and we can do it ourselves. The thing is, to run a validator, that's not necessarily cheap. It can be cheap if we have the burn and give validators, but it could not. So for that, that's the phase 2. That the phase 2 is actually run the validator. So phase 2, it actually runs the validator and checks that you can do that. This is the node. So there are two important things here. One is that we can reproduce this in our computer before sending the transaction, because the transaction itself is deterministic. That's one thing. But there's another thing, that because this is cheap, no one cares if you, like, the node is not going to charge you if you provide the wrong, if there's no UTXO, so if the types you have to apply are wrong. The node is just going to reject your transaction, say, hey, you are missing, the UTXO is missing, like, figure out, change the transaction. And you get a rejected transaction, you can keep trying again and again and again and again until you do it right. That's no issue. But phase 2 actually requires work from the node. The node has to run the validator and actually, like, execute the logic. And that could potentially be super expensive. So the node asks you to give it a collateral. Phase 2, it's potentially expensive. Pay upfront. So the node is not pay upfront. It's more something like, I just created like 5. It's more than pay upfront is it's leave a deposit. There you go. So in these cases, and in phase 2, the validator says, okay, I'm going to run I'm going to run your validator, but you have to give me enough money to pay for the compute time in case you did something wrong and the validator doesn't allow me to unlock the UTXO, because as Lars said before, when we create transactions, there's a small percentage of the transaction that goes to the node to pay for the calculations, for the verifications. But if the node cannot unlock the UTXOs, there's no way for the node to get the value. There's no way for the node to get paid. So we have to leave a deposit. And this deposit is called the name just slipped out of my mind.
Collateral.
Thank you. The name slipped out. So this deposit is called collateral. So if the phase 2 correctly passes, that no one touches your collateral. Your collateral is going to be there in your wallet. But if phase 2 it's wrong, like in phase 2 it rejects the transaction for some reason, it's going to leave all the UTXOs that would have been spent by the transaction untouched because the transaction was not authorized, but it's going to take the money from the money that it needed from the collateral that you deposited. So that's how nodes are protected from being scammed. And I think this was, this is of course, because we should have explained this in the first lesson, but in the prior lesson, but someone had problems that says that the collateral wasn't enough. So this is why you have to have enough collateral. You have to have some sort of collateral to pay in case the transaction is wrong. But if you do things the right way, you shouldn't ever get the collateral consumed, because in phase 1 there are plenty of checks that protect you from failure from phase 2. And if you actually fail in phase 2, it's because you are trying to sidestep the phase 1 checks. So you're being a baddie and you're not being rewarded for it. So yes, that's actually, I wanted to explain time, but I remember that I need to explain this as well. So this is reproducibility, phase 1, phase 2, collateral. And now let's see how we can deal with time. So I just said, by explaining this, that transactions are reproducible. So how come if time is always changing, how come my transaction is deterministic? Because I can just how's this called? No. So if I create the transaction right here and it says all good, but then from the time that it takes some time, let's say sending transaction to node, and right here is the time when the node executes the transaction, and the node says run. So it can happen, and it makes sense that it happens, because like I checked the time, I checked my transaction at some point in time, but the time keeps going, and until I send the node, I will have, no matter what, a different time in the real world. So if for some reason the verification of my transaction depended on an exact point in time, I have no way of knowing if that's going to be reproducible, if that's going to like pass or not. It's impossible with this schema right here. So Cardano has a really neat solution. So in Cardano, transactions, instead of having a single point on time where they are valid, transactions create, transactions say, okay, I'm going to be valid from here to here. This the transaction says I'm valid inside this interval. There you go. So the transaction say, okay, I'm valid inside this interval. So what we can do, I'm guessing you already know, is that we can say, okay, let's create the transaction here. Here and the node checks here. In both cases, I'm inside the valid interval of the transaction, so it's going to be correctly evaluated, and the transaction is going to unlock the UTXO. So this is what we need to do now. Like every transaction, no matter what, has an interval. The default interval of a transaction is from -infinity to +infinity. So it's like every time is fine by me, basically. That's not, in practice, there's a difference between real time and the time that the blockchain follows, because the blockchain has no access to time, so it has to like use its own version, and the blockchain uses again, I lost the word. So I lost the word, but it's going to come back anytime. So the blockchain counts by itself the steps, every step that go, every. Yes, Karina? Or
No, maybe you say a slot, but no.
Slots. Perfect, Karina. Yes, that's exactly what I needed. So the blockchain counts in slots. And right now, the slot of Cardano is calculated, it's like hard-coded as one slot is equal to 1 second. So we can, in our validators, we can use POSIX time, which is like the time from 1990, in 1st of January of 1970 until now, in seconds, something like that, POSIX time, like the standard Unix time. So we can use that, and then it can be translated into whatever we need. So we can use that. We can use that to translate our real time into blockchain time. The thing is, we can change that. Like it can be changed if the algorithm changes. So if we create now a transaction that says, okay, I want to do it in 10 years, 15 years, I want to be executed. But in that time, the engineers figure out that we need to change the slot from 1 second to 0.5 seconds, something like that. now all of a sudden our transaction is not going to work properly. It's going to unlock it in a different real time. So transactions have a limit. Transactions that care, the ones that care about time, that are not like that cannot be executed in an infinite point in time. Those one have an upper limit of like 36 hours, 36 hours, which is the minimum time needed for this parameter and others to change, to have a substantial change in the blockchain. So that's a minimum. We know that at least in 36 hours in the future, it won't change. I'm sure of that. So we can create a transaction taking into account that. But the validator itself doesn't care about that. The validator we can create a validator that unlocks in 10 years. We just cannot create the transaction now and wait 10 years to submit it. We just have to wait until 10 years passed, and then we create the actual active transaction that consumes the UTXO. But the UTXO is going to sit there, protected by the validator that says, okay, in 10 years, no one is going to touch this UTXO. So that's one thing that you have to take into account to time. The bottom line is that instead of specifying specific points in time, we are going to specify ranges in time. We say from here to here is valid on the transaction side. On the validator side, we can just say like this is bigger, this time is after the other, and that's it. I don't care. So that's what we're going to do now. So let's look at this interval. We want to find what is this interval, because we want to provide a date, a deadline, and then we want to check if the validator wants to check if the transaction is being sent, is being run, executed after our deadline or not. If the deadline is here, if here we have the deadline, validator, if we have the deadline of the validator right here, this is going to pass because I'm creating and validating the transaction after the deadline. So my son is not 13 anymore, it's like 18 or 24, 10 to 1, it can execute. But if I'm trying to validate if the transaction is after the deadline, is before the deadline, this is not going to pass. So from the validator deadline to the pass, it has to fail always. From the validator deadline to the future, it has to always pass if the correct person signs. So let's look at this time thing. Let's go to script context, and we have the transaction right here. Transaction, we just use extra signatories, but here we have validity range. Sounds promising, so let's see. Validity range. Awesome. So validity range is an interval of POSIX time. Measure number in milliseconds is 1st of January 1970. It's milliseconds from the 70s. So this validity range is just a different name from an interval of POSIX time. So let's go to interval. Go to interval. So as you can see, the interval is a type that represents intervals. Like, so we can use intervals from many things. In our case, the intervals that we care about is the intervals of POSIX time. So here we have an example of how it works. So this interval of POSIX time has a lower bound and an upper bound, which is this lower bound and upper bound. This is our interval. So the lower bound is it's a value of type interval bound. It's the lower bound is an interval bound. The type of this bound is finite. So it could be either finite or infinite, positively infinite or negatively infinite. In this case, it's finite of value 1, so it's 1 millisecond after the 1st of January of 1970. And if it's inclusive, this is a Boolean that says, okay, this time is inclusive in the interval or not. And we have the upper bound that is the same. In this case, it's finite 10, so 10 milliseconds after, and it's true. So this interval, is an interval that goes from 1 millisecond after 1st of January 1970 to 10 inclusive. So if I create the transaction in 0, it won't pass. If I create it in 11, it will pass, right? Independence of the limit. So here, oh, there it goes. Here we have positive infinity, sorry. And this is not inclusive. And well, we have the constructor interval, lower bound, blah, blah, blah. So we have the value of the transaction. Awesome. We can, like, if we drill down to it, like script context, dot transaction, dot intervals, blah, 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 we eventually will reach to the value that we want. But if we have that value, we cannot do much because we don't know which was the deadline that we chosen. So we have to choose a deadline. And we're going to do the same process that we did for the user. So we need another thing. Actually, this is going to be a bit long. So let's create a type alias. Let's create type, we can say public key hash to make it easy for us, is equal to all this. So now I can just replace to key hash. There you go. So it's nicer now. And I can as well, and now I need to add the deadline. So let's see, deadline, and of the time of the deadline, we just saw that we can use POSIX time. So let's use POSIX time, I think as it is. Let's see. Yes, awesome. So from the ACAN/time, we get POSIX time. So now we have our new datum that has not only the POKey hash of the beneficiary, but also has the deadline. And now we need to do another check. So this is getting a bit hairy. So maybe we should, I mean, we can keep adding more code right here, but this is it's going to be a bit hard to read after if we write a bunch of code like this. So I think we can create a function. We can extract the logic and just leave what is actually explains the logic of the contract inside the contract. So let's create a function called must be signed by or by must be signed by, and this function has to contain like this logic. So so here I'm going to provide this list has, and people that sign like here, and beneficiary. Yeah. So I can just remove this because I'm going to provide the beneficiary. And here I can say, okay, let's use must be signed by. And instead of like naming all this, I'm going to just get the extra signatories and pass it as the people that can sign and datum that beneficiary. Okay, so now it's more clear that we first check if the purpose is to spend, and if it is, we check that it must be signed by the beneficiary. Perfect. So now we need to do a different check, and we can do, actually, we can just start by defining the function that we want to run right here. So we can say function must be after deadline. And this function must be after deadline, must be after deadline. It has to take, what does it has to take? So the range of the transaction and the actual deadline. And I think with those two, we can figure out a way of checking what is inside the other, etc. So we have the deadline. We first figure out the range of the transaction. So let's do that. We have a context dot transaction, because the other option is just purpose, and we know that that's not what we need. And if we go to script context and we go to transaction, we see that here we have the validity range of type validity range. This is what we saw that we needed. So that validity range. Okay, we get an error because like we are missing a parameter. So we have the validity range, and we also have the deadline. And the thing is, we are having here an error. We provided both values, and that's fine, but the formatter removed the squiggly braces. And that's because, I mean, here we have two different expressions, but we just said a while ago that everything inside these squiggly brackets has to be an expression. But we have two expressions. We need a way to combine these two booleans into one. And of course, we can do that by using the AND operator. And this should work. Functions must always be called with all the arguments, comma separated. What did, oh, I added this wrong.
Your skeleton function still doesn't have any arguments. Maybe that's the reason.
Oh, yes, you're right. Thank you. So yes, the expression itself, the expression inside the spend is fine, but must be after deadline is empty. So let's do that. So must be after deadline takes the validity range, and the validity range is of type validity range. So we can say range of type validity validity range. This is not needed. This type validity range is not, the specifying the type is not needed, but it's easier to read afterwards. And we have the deadline that is of type POSIX type. And hopefully, yes, it works. Let's import validity range. Validity. Oh, okay, there you go. So one thing that is a bit ugly is that we have this. I mean, I created initially, I created it like this, and it was like nicer to read. So we check that it must be signed and it must be after deadline. But then as soon as I added, I combined the expressions, the formatter just broke everything. So we have more than one way to combine Boolean expressions. One really nice way is to just provide here in the square brackets, we say, okay, we have an expression and we have the AND combinator. And this should be a comma. There you go. So we use the AND combinator and treat the block, the expression inside the block as a list of Booleans. So this AND is going to combine the Boolean return by must be signed and the Boolean return must be after the deadline. So only if both it's signed and is after the deadline, it returns true. Else, if just one of those are wrong, it returns false. And we also have the OR option, but in this case, we need the AND option. So let's define this must be after deadline. So we have this validity range, and if we go to validity range, I'm going as low as possible so everyone can go with me. So let's see, validity range is an interval. So interval. And we have lower bound and upper bound. So what do we want to check? We want to check the transaction has a range, right? Let's see. The transaction has a range that is valid. But the deadline really only cares if the lower part of the range has passed. So if the range is like 36 hours, but the lower bound is already after it, I don't really care about the upper bound. Like the upper bound, I don't lose sleep if the upper bound is here or here or here. I only care if the lower bound is here or here. Like it must be the lower bound must be after the deadline. So that's what I care about. So let's see. I care about this lower bound. And once we are here inside this lower bound, let's go step by step. Let's see the whole thing. So once I'm in the lower bound, I need to check if this lower bound is finite or negatively infinite. Because if the lower bound is negatively infinite, I cannot ever approve this transaction, basically. So I have to make sure that the transaction is after the deadline. So it has to be a finite transaction. So that's for sure. And once it's finite, we will check if the deadline is before or after. But just to get started, I have to make sure that the lower bound is finite. So let's see. We said that we can pattern match using the when expression. So when, and we have the range. And inside the range, we said that we have the lower bound. And inside this lower bound, we have this bound type. but still is the bound type. So this bound type can be either negatively infinite, finite, or positively infinite. So if this is finite, we name this value. This is the lower bound of the transaction. In this lower bound, we can call it however we want, but we can say, for example, transaction earliest time. And because we're pattern matching, we use the right arrow. And here we're going to do something. And if it's any other, if the lower bound type is anything different than finite, I don't care about it. I'm just going to fail. I'm going to return false. So we have the transaction earliest time, and we have, because we pass it as a parameter, the deadline. And if we check the transaction earliest time, doesn't say it right here. Let's see if I hover. If we check this transaction earlier time here, we're going to see that it's a POSIX time. So this integer is a POSIX time value. And we also have a POSIX time value. And it turns out in Aiken, we can just compare POSIX time with POSIX time, and that's it. So we want to make sure that the deadline is less or equals than the transaction earliest time. And if that holds, we have to import finite. And if that holds, that means that someone is trying to consume the UTXO after the deadline, which is good. We want that. So I think that's it. That's we have our final validator, which is like 40 lines of code, taking into account the imports and stuff. Really simple. The validator itself is here. This is going to be compiled. And these functions are pure functions. And as you can see, I have to provide everything from inside the validator. So the context, transaction validity. So this is going to be eventually like inlined inside the vesting. This is just a nice way to reuse code. Actually, we can reuse it. It makes sense that the must be signed function and the must be after deadline functions are both useful for other validators, right? Because like many validators do these checks. So in that case, we could, if we want to, we could just take this. And if we go to the Explorer, we can start using our, where is it? Assets, docs, validators. We should have a library. New folder. We should have a library called examples Aiken. And in this library that I already lost, we can create any Aiken file that we want. This library doesn't contain validators. It's just helper functions and stuff like that. So we can say utils, AK, utilities, and oops. Let's see if there you go. So these utils, and now I have to import them. Use live examples. Aiken, examples Aiken, and if underscore. Okay, so that's what's wrong. I need to change this to underscore. So the whole point of like doing this, there you go. No. Let's see if I try to import directly. Usually works like this, but maybe I'm missing something. Let's see. Let me check. Leave the name util okay. I think it's fine. Leave examples Aiken utils. This thing is not picking up the file, and I'm not sure why.
Do you need
You-
something like an export list or something like that, or an explicit export, or
No, it's
does it
it's
export
automatic.
everything?
Yeah, I mean we can manage that, but there's no need to actually.
Well, that's this pub, probably the pub function part.
Right. Yes, I have to make them public. Let's see if that works. Right. Yes, it might be that. Thank you, Lars. I have to make the functions public, that's for sure. Let's see if it now works. There you go.
Huh.
No. I have a different
No?
error. Good. That means that now the LSP knows that this is an Aiken file and it can work with it. That's good. We have validity range. And now we have. For some reason, it needs like the whole
POSIX time as well.
list. What else? Of finite. We have to re-import everything. The cool thing is that we can delete it in our validator. I think fine. Looks fine. So now must be signed by let's try directly. Use leave. Let me check how I import it. Here public. I use no, I don't use it. Aiken dictionary. I don't recall like where do I use them? No, I already changed. I know that this Aiken is really particular with naming. Really particular with naming. So maybe I'm doing something wrong on that regard. PPP contrast naming. No, okay. I have to have like this here.
They say the lib, you don't need the lib. in the example on the documentation.
Okay, let's try. Use a no. See. Let's try to like read.
Where exactly is your helper module? What's it called?
It's live example second. It's on the same level as validator, so I think that's okay. And then I call this utils file. So I have to call utils, but it's weird that I think I broke the LSP. So let's restart Dino. We don't have that, so I just reload. Let's see if that fixes the error. I have to get this must be, there you go. Let's see. You know what? I can just search live. Utils. Util. No. Seems that I haven't used it. But I already did, and it was imported automatically. Use. Let's try live example. Okay. No idea. No idea what this not working. But I mean, this I'm sure a silly thing. I'll figure out. But maybe we can take a break because we have almost 2 hours been here.
Mm-hmm.
And in that break, I can see if I can figure this out.
Okay.
Oh, there you go. It worked. For some reason, it started working without changing anything.
Yes, was only you needed not the leaf, only
Yes, not the lib.
the name. Yeah, the
Right.
name for the folder you have inside the leaf. Because
Thank you.
because for the folder, I can take the old folder you have into this folder called the leaf.
Right. Okay, so it was without the leaf. But the cool thing is that if it works, it is imported automatically. Awesome. So there you go. We have our validator as a really simple one, as you can see. And let's take a short 10-minute break, maybe, or 15, I don't know. And then we can use it.
Mm-hmm.
Yeah.
Until 10 or 15.
For me, I think 10 is better, so we can cover more.
Okay. And 10 to the hour, we start again.
Okay, perfect. Thank you. Thank you, everyone.
Thank you.
Okay, we're back, everyone. We have a question. What is the default behavior when we create a new transaction with regards the intervals? What are the default values of the interval? How we can change them? Yeah, so we're going to see how to change them. The default is that the transaction is valid from -infinity to +infinity. So there is the default interval is all the possible interval, the biggest imaginable possible. That's the default. So when you create a transaction without specifying anything, it's assumed that the transaction has an interval of all the time. So how we can change, we're going to see it right now. So now we
Just
have
want
a
to
valid.
mention,
Yes.
sorry. That's true what you say if you use the Cardano CLI, for example. But I think wallets sometimes have a different default. So I don't know about Nami, but Eternal, for example, I think it's valid for 3 hours or something. So they do set the, if you don't do anything, they do set like upper bound.
Right.
And I think the reason is that, I mean, if you don't restrict it at all and you send it, then you can never be sure whether it will fail. I mean, it could happen that for whatever reason, like in 2 years, it suddenly goes through. And normally, I mean, you want to, if it fails, you want to be sure that it failed. So if you wait a day or whatever and it didn't happen, then you want to be sure that it will never happen. So I think that's why these wallets do it, that they do set the different default.
Right. Makes sense. Makes sense. So yeah, you can, let's see how we can actually like set the intervals. In Lucid, at least in the library that we were using, like the default was, I believe,
Yes, probably it's unrestricted.
unrestricted. Exactly. So let's see. There's a bunch of things we need to do now. I already have money in Alice and Bob wallets, and I already have the documentation running. So now I can run script, off-chain, check wallets. Yeah, so both Alice and Bob have money, not much, but enough. So let's say that Bob wants to send money, wants to lock money in this vesting validator from Alice to take out like several minutes after, because like we don't want to be here for days. So let's see. Let's go to off-chain. We have Antonio and Karina have already pre-written this for us, kindly, so we don't have to write the whole code from scratch. We just have to go over it. So let's see. Let's see how we can lock ADA in the vesting validator. So let's go to the top. Here we are creating a type using TypeScript, using this type box library. The point of this is to, I mean, we could just choose binary code straight up right off the bat and stuff like that, but it's cumbersome to work with. So these libraries, like Lucid and other, provides like helper functionality. And so this datum schema that we have right here tries to represent this same vesting datum that we have right here. So we have the type vesting datum that contains inside the beneficiary and the deadline. So this is what we have right here. We have the datum that inside has the beneficiary. In this case, the beneficiary is just bytes, an array of bytes. And the deadline is an integer because I think I never showed this, but if we go to the documentation, wherever I left it, Because but at this point, I don't know where I left it. So if we go to the documentation and we go to POSIX time, we see that POSIX time is just an alias for integers from unbound integers. So that's why we have here this integer. So it's just the same datum. We create the structure of chain, so it's easier to create the transactions. And this is part of the same thing. So here we use Alice PokeHash. We load. This is same as the, I think 2 days ago. We read the Bluetooth JSON file. We create the spending validator. In this case, we want to use the lesson 2 vesting.vesting validator and calculate the validator address, and we print it. Then we prepare the datum. Like we have the shape of the datum, but we don't have the values of the datum yet. So we obtain Bob's PokeHash from his private key. We could also as well obtain it from the wallet that it's already loaded. So we have we have Bob's public key hash, and we want to calculate the deadline. The deadline is now plus some extra time that we want to work with. So this date.now, it returns POSIX time. So we have to add whatever time extra we want to work with. So if we do this 1 minute, it will likely always work, because between like we create the transaction and all the things, the minute will pass. So let's change this to 5 minutes. So we're going to put the deadline 5 minutes from the time when we create the transaction. This is the deadline that we provide to the validator, so to the datum of the validator. So the validator is going to be checking that 5 minutes from the time that it was created has passed or not.
Just a question. Sorry,
yeah.
I mean, one always has to be careful. I mean, I've often made that mistake in the past. I mean, POSIX time, I mean, some people use seconds since the 1st of January 1970, and some people use milliseconds, and you multiply by 1,000. So I assume that means that Bluetooth uses milliseconds, right?
Yes.
And JavaScript as well. So the date now works, or does that have to be multiplied by 1,000?
Yes, actually, I searched for it yesterday just to double check, and yes, it returns milliseconds.
Okay.
Yeah.
I mean, I often use, I don't know the site by name, but if you Google POSIX time online or something, then you normally find a site where I think there's something, or POSIX online, POSIX time online, something like that.
Yeah. Yes, I have
no, actually,
a
yeah,
converter.
that one, and I think that supports both milliseconds and seconds, so you can like check what.
Yeah, I think this is seconds. Yes, it supports Unix times and seconds, milliseconds, microseconds. And here the datetime now, I changed this code and printed, and yes, it was milliseconds. You can see it here as well.
Right.
Yeah. Just to be sure.
So that's I mean, I specifically find that confusing because I mean, we are not using Haskell anymore now, but if you use Haskell has a very popular library for handling times and dates and stuff that's called time. It's on Hackage, and that also has a POSIX time type, and that uses seconds, not milliseconds. I mean, you can have fractionals, but the unit is basically seconds. So you always have to be very careful, like converting with these times, because it's easy to like get a factor of 1,000 wrong Just
Right.
wanted to caution. I mean, it's fine if it works with JavaScript, but if you use another language, for example, you have to be careful that you like convert it correctly to Pluto's POSIX time.
Yes, this is, you always have to test. I mean, here
Yes.
we chose, we chose to write the off-chain code right after we have the validator, but like in reality, it's way more important to actually test so you should write a bunch of tests before anything else.
Just imagine you deposit 1 million ADA for your 13-year-old son, and he is supposed to get it when he's 21, and then he has to wait 21,000 years or something because you make a mistake. That would be unfortunate.
Yeah, poor guy. And you cannot take it back. I mean, at least with our setup, there's no way you can take it back.
Exactly.
Maybe that could be the homework, how to change
Yeah.
the validator so you can take it back if you messed up.
Right. Actually, I mean, at this other company I work at, we do use vesting, and we have this cancellation feature, but it's a bit more complicated because it's also, I mean, what does vesting mean? I mean, normally it means you send somebody money, but he's not supposed to access it before a certain deadline, but he is supposed to be sure that he gets it. So if you can unconditionally cancel it again, it's sort of pointless because then you could just keep it with yourself and then give it to him on his birthday in 5 years or whatever. So what we did is actually 2 deadlines, basically one until that you can cancel, and then after that you can't cancel anymore. So the idea there was that if you make, I mean, if you make a mistake somehow with a transaction, then you have a day or so to check it and cancel it if it was wrong. But then once that first deadline has passed, it's locked forever. I mean, until the second one is reached. So yeah, you can make that like arbitrarily complicated. But would be nice homework to add the feature that the person that deposited it can actually cancel it.
Right. Maybe we can make it that you can cancel it after, like a month after the initial deadline.
Yes, that's also possible, of course. So if the beneficiary doesn't collect in a certain time, that you can get it back. I mean, that would also be useful indeed. Yes, that's a nice idea.
Nice. So, okay, no questions so far?
No, in the chat.
Perfect. Thank you, Karina. So we have these 5 minutes of extra time. We create the deadline by adding the POSIX time in milliseconds from now plus the extra time, and then we create the datum. And we use this data tool to transform this JSON-like object into Bluetooth-like object. And we specify that the type that we want is the datum, which is the one that we specified at the top. So now we have this value of type datum with the correct shape and correct type that we can use in our transaction. We create the value, which is just 10 ADA, I believe. And then we can prepare our raw transaction. The raw transaction, we said before in the prior lecture, we're just sending money to the validator, so the validator doesn't really care about it. So we just pay to we create a new transaction, pay to the contract. What do we pay to the contract? Well, to this address, the validator address that we just created based on the vesting validator right here. So this validator, there we go. This validator address with the datum is going to be inline datum, so we can inspect it later before consuming the transaction. Inline datum and the value that we chosen to lock. So this could be anything. We chosen 10 ADA. And then we complete the transaction, we signed it and submit it. That's it. So this is how we lock. Alice is going to lock. And another thing that we have here is the unlock ADA from vesting validators. We're going to go over it later, but first I want to run it so you can see that it fails, and I don't want to explain things for over 5 minutes and not be able to showcase that. So first, let's run the script of chain lesson 2, and let's lock ADA in the vesting validator. So as soon as we run this, the time starts counting. So let's run this. There you go. We have the validator address and we have the transaction ID. Let's make it bigger. So now I'm going to try to consume it right now, just to show you that this is going to fail. So run script of chain lesson 2, unlock ADA from vesting validator. And if I run this, this should fail because we haven't had 5 minutes yet. And says that UTXO is not found at the validator. So it's not that it failed because the validator rejected it, it's that it failed because the original transaction hasn't been settled yet. We can run script of chain lesson 2 and check vesting validator. There you go. We do have, so if we run it now, unlock ADA, we get an error. There you go. We have the UTXO that we wanted to consume, which is the same as prior, the first one. And we got an error because we're trying to spend the UTXO. Here we spend the UTXO, but the provided Bluetooth score called error. This is not really useful, this error, and there's a reason for that. It's expensive to have validators running in your, it's expensive, the real estate, the byte real estate in the Cardano blockchain is expensive, and running validators is expensive. So a lot of code, all the code that we can avoid to upload and to run, we should be avoid. And one of those things is the proper error messages. So in our case, we don't have any tracing and any error tracing in our validator. We can have it though, if we want to, but it's going to make our validator heavier. But if we are just developing, we're not like doing the release version yet. One cool thing we could do, for example, if this validator fails, it just failed, this validator just failed, and we have no idea if it fails because it must be signed, because the wrong person signed, or there was this missing signature, or because of the deadline. So it fails, but why it failed? So during development and during testing, and we're going to cover testing in a future lesson, we can use this thing called error tracing, and all you need to do is for every Boolean that you end up with in your validator, you add a question mark at the end, and here and here. And now, if it fails during development, during testing, I will get, hey, it fails because the must be signed function didn't return a true value, it returned false. And the same for the must be after deadline. So this is really nice, really easy to set up, like just add question mark, whatever you need a question to know if it's true or false, and that's it. And we're going to use that for now because we are not testing, we're just running in the actual blockchain. All the traces get erased by default. You can avoid that, but as I said before, that's not a good idea because it makes everything more expensive. People have to pay more ADA to run your validators. so not a good idea. But for development, they are beautiful. So we locked the ADA, and we were trying to unlock. It got this error because we know that we are signing it correctly. So it's because the deadline hasn't passed yet. So let's see what did we try to do to unlock it. So let's go to unlock ADA from vesting validators. And let's see what we do. So we have the same structure for the datum. In this case, Bob loads the wallets. We load the same validator. This is the same as before. In production, you shouldn't repeat everything in every script. We are doing this when doing it this way, so you have like atomic scripts that you can copy and paste. So we have the validator, we have Bob's wallet. Then we get the address of the validator and all the UTXOs inside this validator. Then we get the public key hash of Bob from his secret key. And this is when we get the current date, so the current POSIX time. In this time, we don't want to modify it. We just want to get like the real one and maybe change 1 minute, so to make sure that it doesn't like to make sure that there's no errors because of just 1 minute of difference or something like that. Because usually this is something you log for hours or days or months of years. So 1 minute is not really something you really care about, usually. So in our case, I just get the current time. This is the time when I'm trying to unlock the transaction, the UTXO. And then I filter the UTXOs. I say all the UTXOs that are sitting in this validator address. There could be hundreds. I just care about the one specific that is for me. So I just say, okay, for all the UTXO, find the one UTXO that then parse the datum of this UTXO. And if the beneficiary inside the datum is the same as my pub key hash, keep it. If else, like there's no UTXO for me, there are UTXO for other people, but not for me. So there's no way I can unlock them. So I just fail. I say, okay, UTXO not found. Like there's no validator for you. Sorry. So now we have the UTXO we want to consume. With the pub key hash, the time, we have everything. So now let's answer the question that we have earlier: how we can how we can manipulate the time range of the transaction. So first, we create a new transaction. We add a signer. This is important. We have to make sure that the body of the transaction contains the signer. So we add a signer for the transaction. In this case is Bob. So this is why then we can, it was here. This is why then we can access Bob's pub key hash inside the validator's context. Then we state what is the valid time range for the transaction. In this case, we use valid from because, as I said before, we don't really care about the end of the transaction, the end of the range. I just care about the beginning of the transaction. So if the range of the transaction is as a whole after the deadline, that's good enough for me. So that makes sense, right? If part is on the deadline, if part of is before and part is after, or part of the whole is sorry, before, if part is before and part is after, or the whole thing is before the deadline, I have to reject it because I have no idea if it's in between. I have no idea to check, so I just have to make sure that the whole range of the transactions is after. So we use this valid from. So valid from says, okay, from now, from the point, the value that I'm going to provide up until whatever the maximum allowed, it's the transaction is fine. So in this case, my range intuitively will be like from now until infinity, right? Until as much as possible. And instead of doing just now, I do now minus 1 second, just so like to make sure that this 1 second that I do the transaction doesn't invalidate locally in my machine.
Looks more like 1 minute, but I think that's also fine.
Yeah, maybe. One.
I mean, you multiply by 60, not.
Yeah, you're right. 1 minute. So that's if we do now, it should work theoretically if we just do this, but I think it might not work, maybe too risky. So it's just better to do a small change, I think. Yes, Lars?
No, I mean, I think you're right, because I mean, could be that your clock in your computer is off by a second or so. So if it's, and then it would basically be a second before the true time, and then if you submit it exactly at the deadline, then it could happen that that it fails, even though now, I mean, your clock says the deadline has been reached, but it hasn't really. So I think it makes sense to subtract a couple of seconds. Whether you need a minute, I don't know, but a couple of seconds certainly makes sense.
Yeah. Awesome. So that's I'm not sure who asked, but that's how we can this in this case. Remember, we're doing off-chain. We're specifying properties of the transaction, not the validator. So the transaction goes from now until infinity, and if we create a new one, the validation range is going to change to the new one. So we can reuse this as many times as needed, but the validator is going to allow me to unlock just a specific point that I said so. And the rest is the same as before. We have to, in this case, collect a UTXO from the validator, and we provide a list with, in this case, a single UTXO, the one that we care about. As a redeemer, we provide data.void. As you can see here, we are not really using the redeemer. We have this generic data. We could have used void if we wanted to. Doesn't make a difference in our case because we're not using it. So we want to collect from, and we attach the spending validator because now the node has to run the validator to make sure that I can actually consume the UTXO. So we have to actually provide, not just send something to the address, but actually provide the validator itself for it to be run by the node. And same as before, we complete, signed, yada yada. So now if we run again, the same, it already passed 5 minutes. So now we should be able to unlock ADA. Actually, let's first, before I unlock it, let me I want to see the datum in the Explorer. Copy. So let's see, Cardano scan. What did I do wrong? Let's take the address. Oh. The vesting validator address, copy. I want to show you the datum before we consume it. Oh, we're in
We are
mainnet.
in mainnet.
Yeah. Thank you, Karina. We're in mainnet, so we need to go to preview. Okay, so we have a validator with 10 ADA, which is the thing that we just sent. We have a transaction count because the first time we use this. So this is the one that I did 14 minutes ago. So the deadline already passed. And if we take a look at the transaction itself, we see UTXOs. As input, we have Alice wallet that has 27 ADA. And as output, we have the address of the validator that has the 10 ADA and Alice's wallet again that gets the change, 27 minus 10, 17, there you go. So this is the UTXO that we created in the validator. And if we click here, we see that we have the hash of the datum. But because we inlined the datum, we also have access to the actual datum, not only the hash. So if we click here and inspect, we see that this looks oddly familiar, kind of. But the thing is, we created, we go to the top, we have this datum that has the beneficiary, that is a bunch of bytes, and the deadline, that is an integer. And here we have the same. We have a single constructor that has two fields. One is a list of bytes, and the other is an integer. And this is the actual POSIX time of the deadline. So, as you can see, at least structurally speaking, it looks correct. But just to make sure that it's correct, we have to actually run it. So run script, unlock ADA from vesting validator. Let's hit enter. We want to consume this datum with 10 ADA, and the transaction was submitted. Copy. Let's go see this transaction. Search. It's not there yet, but if we run script off-chain lesson 2, check vesting validator, we see that the validator doesn't have any UTXOs anymore. We consumed it. And Bob off-chain check should be richer by now. 15 ADA. Let's see. Let's refresh. There you go. So we have 0 confirmations. We got the block as soon as it was created. So we are at the tip of the blockchain. So the summary is that the address or the UTXO, we consume 10 ADA from the UTXO from the address of the validator, and we gave 9.8 ADA to Bob. If we check the UTXOs, we see that Bob has 149 ADA, and the validator had 10 ADA. And these two are the UTXOs, the unspent transaction output that is going to be spent in this transaction that just occurred. And this is the UTXO that was the output that was generated after the transaction. In this case, we have 2 inputs and 1 output because we consume the one in the validator. We consume one of Bob's UTXO to pay for the transaction, and we took a small fee for the transaction, but added the 149 and 10 ADA together to give 158 point almost 9 for Bob. So it all worked flawlessly, if I might say. So let's see what else.
Nice.
Yes, Lars.
No, I just wanted to congratulate you to this flawless performance.
Thank you. Thank you. And thank you, Antonio and Karina, for helping as well. So now let's do something a bit more complicated, but with almost the same result. So let's see. Let's say we can have several reasons to avoid having, for example, one single vesting validator with thousands of UTXOs being consumed by everyone at the same time. So there are many reasons, but let's look at it from the point of view of the person that generates that actually is doing only vesting for now. So let's say that I want to create this vesting, but not for like some kit until it grows up. But I have a company and I have 100 employees, and I want to give them like some tokens related to the company that they can spend sort of like if it were stock options. So the thing is, if I do it right away and my employee doesn't like me, he will just consume the UTXO and run away from my company, and I will be like lost without my employee. So one thing that companies do is, let's see if we can have. One thing companies do is to say, okay, I'm going to hire you, and I'm going to give you all the stock options, the tokens that I promise. I'm going to give them to you, but not right now. Just to make sure that you don't run away as soon as I give it to you, I'm going to give you 25% in the first year. Let's see here. Let's see. It's year 1, 25%, 25. And I can do like differently. I for example, I can do like some consistent vesting, and the percentages that don't need to be consistent, but they of course need to add 100 eventually.
Just want to mention that I think the main reason is not necessarily that the people don't run away. It's that that not too much stock is dumped at the same time or immediately after launch. I mean, often it's, especially with these crypto projects, they have these, whatever it's called, some initial coin offering or so.
Yeah.
And then people buy cheap. And I mean, a lot of them would like to dump immediately. I mean, they buy it, and then as soon as public sale is on, it's basically tradable. They dump everything. And if a lot of people dump their tokens, then that, pushes the price down because it's a supply and demand. So if the supply suddenly goes up, then the price crashes. And in order to prevent that, I mean, this is one way that projects use to prevent that everybody dumps their tokens immediately, to use this vesting. I mean, they have them, but they can't access them. They can't dump them immediately. So that's, I mean, or at least it's another reason.
Right.
And of course, also, as you said, I mean, maybe not running away, but like, especially for employers, if they have a vesting period of a couple of years, then it's only worth something if the token is still worth anything in 3 years or 4 years in your case. So so that the team has an interest in making the project a success, so that the token is valuable after 4 years. So it's basically an incentive for the employees to make the token as valuable as possible and the project as valuable as possible. So that's the other reason.
Nice. Yeah. Thank you, Lars. Yeah, and of course, it makes sense to give. I mean, I was really thinking of like fun companies like Meta and stuff. Like they give you, they do these things as well with
Yes.
stock options. But it's also like you could just pay more to your employee, but that by giving the employee stock options, you get him, like as Lars said, more interested in that the company is doing fine, and also you prevent these job hoppers that are not really interested in working for anyone really or doing anything, and they can just hop from job to job and live from that, from the initial signing bonus and stuff. You can also prevent that.
Yes.
So the thing is that we need to do this, right? We need not just one UTXO, but we need 4 UTXOs, and the 4 UTXOs are going to have different deadlines. So we could create, if we have 100 employees, and we have to create 4 for every employee. So we have 400 UTXOs sitting in an address. That's not a big deal, but maybe other companies want to do it as well. So they all start dumping their UTXOs in the same validator. We have like this validator with thousands of UTXO that you have to swap through. And so there's a better way. Of course, this is not the main reason that the mechanic that I'm going to explain you exists, but it's one that makes sense in our context. So let's see. One thing we could do is to make the actual address of the validator depend on the values that we provided, depend on the beneficiary and the deadline. So let's see. I'm going to delete this. And I'm going to I'm going to copy and paste the same validator that we had just before. Where's the rename? Here. And here we can put same as before, just in case. Parameterized testing.
You want to make it parameterized by both now, by beneficiary and deadline?
Yes, because it's easy, but because we already have the type. But you want it.
Right. No, I mean, I don't want to. I mean, probably you will say that anyway, because I think practically it would make more sense to only parameterize it by the beneficiary and not the deadline, because otherwise it's difficult to find it for the beneficiary, because then he has to know the exact deadlines that are there for him. Otherwise, he can't compute the address, right?
Yeah.
But it's fine. I mean, sure, it's easier to first do it like that, and then we can later do it or as homework. So
yes, and actually, it's so quick that we could do both right now. Because like for one thing, so we want to the validator address to be specific to this vesting datum type. So we're going to, instead of provide this vesting datum, this type as a datum, we can provide it. Let's remove this. Let's do something that we don't care about, data. So there you go. Now, if we leave it like this, we have no more access to the beneficiary and the deadline. So this won't be able to, like, this won't work. We don't have the information. Like, there's no datum that beneficiary, right? So we have to provide it somewhere else. So we can sort of like hard code the information into the validator by making the validator a function that takes some parameters. If we just do the same as before, we could just datum, vesting datum. That's it. That's the whole change we need to do. We just need to take whatever it was in the datum and move it into here, and we have a parameterized datum. But that's technically it. But of course, this is not a datum anymore. So we have to change a bit the naming, right? So let's say that we want to call this vesting parameters. And we can change the constructor. And actually, this constructor, because it's named the same as the type, can be removed. So we can do this. And this is the same as before. And same with the other one. So just for consistency's sake, because there's just one constructor and it is named the same as the type, we can use this shorthand for the type. And now we have here in the parameterized one, we don't have this anymore, so we have to call it vesting. Oh my god! So vesting param, and here we can say params. And now there you go. We don't have datum anymore, so we have to change it to params. Oh. And at the end, if I save, I'm going to get another error. The datum is not correct. So params.deadline. There you go. We have a parameterized validator. Super easy. But we have to change now a couple of things in the off-chain part. So we have to provide the parameters, not when we create the transaction. We're going to do it in the process, in the same script. But now we don't have to provide the values when creating the transaction, but we have to provide the values to create the final script that then we have to create transactions. We want to send and consume from. So we have to apply these parameters to then get the validator. For now, we just have a bunch of code that is potentially a validator, but it needs for us to provide the parameters for it to actually return us as a valid validator, correct validator. In our case, we provide both the beneficiary and the pubkey hash. But as Lars says, I'm going to just go over this quickly because I don't think we're going to have enough time. Another alternative will be to change this whole thing to beneficiary pubkey hash and put the deadline POSIX time right here. So now we split the responsibilities. Now we have to provide the beneficiary to create the final validator. But when we create the transaction itself, we have to provide different deadline every time. And this will change. These params not necessary anymore because the beneficiary is right there, the deadline as well. Just for completeness, this will be the final, and the vesting params wouldn't be needed anymore. So this is what Lars referred to earlier. But we already wrote all the off-chain code for the other case. So we're going to go back to the original one, that we just ignore the datum completely, and we provide vesting parameters, the beneficiary and the deadline both as parameters. So we have our final validator. And let's see, I want to use it. So in our case, we want to first lock ADA in the parameterized vesting validator. To lock ADA, we do the same as before. In this case, is Bob, the one locking. So Bob is locking, is the one that is creating the UTXO at this new validator. We provide the 5 minutes, 5 minutes after the deadline. The 5 minutes, the deadline is going to be 5 minutes after the time we create the transaction. So the deadline is now plus 5 minutes. It's important because now we are parameterizing it, that we have to save this deadline, because now we need the deadline. We need the actual deadline that we used to create it. We need it to create the final validator by the time we have to provide the validator. So we have to save somewhere this deadline, because without this deadline, we cannot construct the final script. So we print the deadline, and then we're going to copy it. And we have Alice's, yes, we have Alice's Pookie hash. Now we are going to create the parameter. This is a different way of creating types. In this case, if you recall, I'm not sure if I still have open the tab, but I did have, no, I don't have the tab open anymore. Here. So we have this constructor 0 and then the fields. This is an actual structure in the blockchain. So we can do the same. In this case, we can just construct it directly without any higher level stuff. So we can just say, okay, let's create a new constructor 0, which is like just one, the type has just one constructor, so it's just 0. And inside it contains the Pookie hash and the deadline as an integer. So here we have the parameters, the same that we used for the datum, but now we are creating it as a parameter so we can after apply it, and we're going to apply it like right below. So we load the Plutus.json that contains all our compiled code, and we create the spending validator. But in this time, when we create it, we don't just use this Plutus JSON that filter blah 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 dot compiled code at the end. We don't just take the compiled code that we used to take always, but now this compiled code is the first parameter of the apply params to script function. This apply params to script takes a Plutus script and the parameters, applies the parameters to the Plutus script to give us a new fully applied Plutus script. This is a small difference between the prior and in the latter. If we just want to use like we did for the regular vesting, we just want to use the compiled code itself, it's going to be missing the parameters, so it won't work. So we have to apply the parameters, and that's what we do. We create the new validator by applying these parameters that we just created with Bob's Pookie hash and the deadline to the original compiled code. So once we have the final validator, we should call this final validator. Once we have the final validator, now I can get the address, I can create the value, and the transaction itself. The transaction is the same as always. Like if we create a new transaction, we pay to the contract, to the address, we inline this datum, but I mean, we don't use the datum in this case, so we just we don't care about it, but we just provide the void datum and the value that we're going to lock, which is again 10 ADA. We complete the transaction, sign it, and submit it. So let's do that. Let's run scripts, off-chain, lesson 2, lock in parameterized validator. As soon as I run this, we are going to get it printed, the time that we used to create the UTXO, and from then on, it starts counting the 5 minutes. So I'm going to do the same as I did before. I'm going to quickly run things so I can show you that it will fail, and then I'm going to go over it. So let's do this. There you go. So this is the POSIX time that we used for the transaction. And if we go to unlock ADA from parameterized vesting and we look for it, here we have the same parameter. In this case, we have to replace it. I'm going to explain this later, but we have to replace it with the new POSIX time. And if I try to run script off-chain lesson 2, unlock ADA from parameterized vesting, it found the UTXO. So we have the actual UTXO that we need to consume. As you can see, the datum is nothing compared to the prior. It's super small because we don't use it. So we found the UTXO that we wanted to consume that has the correct beneficiary, but we couldn't consume it because the validator, the Plutus call called error. The Plutus call rejected our transaction. So let's see how that works. Another thing that we can do is we can check. We can run script off-chain lesson 2, check parameterized validator. But if we do that, we have to go to the check parameterized vesting, check, yes, parameterized. And we also have to replace the deadline here because we have a different one, the one that we just created. So if we do that, we'll see that there is this transaction has 55CE9, 55CE9B. Perfect. So we can inspect what is inside this validator because we are again applying the correct parameters to the code. So let's see how we can unlock the ADA. So to unlock the ADA from this parameterized vesting validator is pretty much the same as before. We just get Bob's private key, Bob address. We select it as a wallet. So now we are Bob. We get the current date. Now we create the new parameter. In this case, we already know we don't have to dynamically generate this. We already know this because we are trying to consume a UTXO that it's already in the blockchain. So we have to provide the correct POSIX time. If we change just one thing here, it will break. So we won't be able to unlock because it won't even find the correct validator. So we apply the parameters, same as before. We query the UTXOs. If if there's no UTXO, it means that we haven't created it yet. We know whether that we did. So this shouldn't fail. So we have all the UTXOs that should be consumed. And then we create the transactions to consume it. It's the same. This one is even smaller than for a regular vesting because we already did the hard part of applying the parameter. So now we can just add the signer, valid from now minus 1 minute until whatever in the future. We want to collect from this list of UTXOs that we just now took. And as you can see, we're not filtering here. We don't need to filter because we know that like we are the only, the validator itself only has this parameter. Like the parameter contains both the beneficiary and the deadline. So it can only, based on our code, it can only be one, because as soon as we create two, we get two different dates. So it's two different validators. So there's no need to filter. It could be either 0 or 1, basically. So console log, add Bob as a signer, valid from, we collect, provide this empty datum because we don't care. We attach this pending validator that we already applied the parameters to, complete, and then same as always, sign and submit. It already passed quite a long time, so we should be able to unlock. Not yet. The provided protocol called error. We found it. Yeah.
I just have one question. This collect from script in collect from UTXOs in Lucid.
Yeah.
I mean that takes an array of UTXOs, right?
Yes.
So what happens if there's more than one? Does everyone take the same datum? Because I mean only one datum is specified. I mean in our case there is only one, so it's an array with one element, right?
Yeah.
But
right.
I mean I find that a bit strange. I mean it would have been more natural if it was an array of pairs. I mean of UTXO and datum or something. I wonder what happens if there are more than one that like have different datums. I mean, then you probably have to do it separately. I mean, it's weird. I find it weird that it takes an array of UTXOs and not just one UTXO.
Right. Here it says that it takes the datum of the UTXO. We're not providing the datum. We provide the redeemer. And for each UTXO, we get the datum of that UTXO.
Sorry. Yes,
so
yes.
We use the same redeemer for all of them.
Oh, you wrote that, or no?
No, that's Lucid.
Lucid.
This is Lucid. So we provide the redeemer for UTXO. If the UTXO has datum hash, doesn't have hash, or has hash but doesn't have datum, we get the datum, parse it, and then assign UTXO that datum. And then
right, and we use the same redeemer, and we use the same redeemer for all of them.
It looks like it's because here we apply the redeemer. Here we apply the redeemer, and we don't change anything.
Right, bit strange.
So we apply the redeemer to all of them, or to all of the UTXOs.
Can you go back? Oh yeah, no, it's fine. Sorry, yeah, okay, fine. Yeah, it's a bit strange, but whatever. It's what they do.
Collect from UTXO.
I mean, I find it a bit weird that it takes an array of UTXOs and not just a single UTXO. In the case of script UTXOs.
Right.
But fine.
I think it gives you more. I think it's fine because it gives you the option to unlock more than one with the same redeemer. But if you need a different one, you just do that collect again.
Right. And it's of course useful if it's not a script. I mean, if it's from your wallet, then you can just, like we did last time. I mean, you look at all the UTXOs at your wallet and then you just collect from them to pay for transaction fees and so on. Right. Yeah. Sorry. Okay.
Yes, redeemer as undefined.
Yeah,
Yes, I think it makes sense. Gives you more flexibility.
yeah, true.
But it didn't work, so I have to run it. There you go. Enough time passed, and
Yeah.
eventually, there you go. So now let's preview our final transaction. It's not there yet. Run script, off-chain, lesson 2, check parameterized. Yeah, we already consumed it, so should appear here eventually. There you go.
Right.
So, yeah.
No, nice.
So we have 0 confirmations. Again, we are at the edge of the blockchain. We consume from a script. This symbol means smart contract address. It's a script address. We consume Temeda and give to Bob 9.8. The UTXOs, as you can see, the datum hash, it's an empty, useless, empty datum that doesn't do anything because we don't need the information in datum anymore because it's intrinsically hard coded in the validator itself. And that's it. It's the same as always. Bob provide its own UTXO for the fees. We consume this and we get the final result. We get, this is the actual bytecode of the contract. You cannot use this one again, but if you could copy and paste it and run it again, if you could actually reuse it. And here we have the collateral. As collateral inputs, Bob just had one UTXO. So Bob provided his own 158 ADA by itself as collateral. In our case, if we consume, like in both cases, if it's successful, the validation, it consumes this 158. And if it's not, it consumes this 158 and gives you the change. But you could, because it's not that expensive to run a validator, you could create a specific UTXO, and plenty of wallets do it. Actually, I think I have in NAMI you have this option, collateral. As you can see, you adding collateral in order to interact with Cardano smart contract. The recommended amount is 5 ADA. So you can create a UTXO that holds only 5 ADA and always use it as collateral, and it will never be, realistically, it will never be consumed because the transaction will always succeed. Because else, if it doesn't succeed, it fails in phase 1 and it doesn't charge you anything.
Right.
So,
The
yeah.
wallet just has to be careful that it doesn't spend it.
Yes.
I mean, Nami, for example, does that. I think Eternal used to do that as well, but for the last couple of months, they messed up somehow. So now it happens in Eternal all the time that you have to set a new collateral because it spent your old one somehow.
Oh.
I mean, the idea was that you have this one UTXO with just ADA, 5 ADA, and then you always keep it apart. You never use it as input to a transaction, only as collateral. And then that's fine. But then you have to be careful that you never use it to pay fees or something, because then it's gone.
But that's usually a wallet thing. Like
yes. Normally the wallet takes care of that. But if you use like explicit addresses with explicit private keys and so on, you have to like somehow manage that yourself to make sure that you always have collateral.
And that will be it for today. We have 1 minute It's 4 questions. Let's see. Looks like we don't have any questions, but anyone? Awesome, Samsung.
I just want to reiterate that I personally feel you should parameterize it like this other option, beneficiary as a parameter, but the deadline in the datum. Because
Yeah.
this way, if you, for example, forget the deadline you set, I mean, you did write it down, but if now your computer crashes and you didn't write it down, then it's almost impossible to find that UTXO again. I mean, not really, because you can look, I mean, in the Explorer, you can check for, but even then, I mean, it's, even if you find the UTXO, it's not clear. I mean, you have to reconstruct the deadline somehow, and you can't because it's just a hash. So there's certain risk that you will never be able to unlock it if you forget the deadline.
Mm-hmm.
And it's also, I mean, depends on the scenario. But for example, if you do this thing that you pay your employees or whatever with this contract, then, I mean, you must tell them the exact deadlines. I mean, you basically send them email and say, okay, I created these vestings for you with these specific deadlines, and then they have to like paste them somewhere. So whereas if you only parameterize by the beneficiary, then it's easy. Then each employee knows his own pub key hash, and then he can easily compute the address for that, and then he sees all the UTXOs for different deadlines, and then he can check and unlock accordingly. So in my opinion, that is the best way to parameterize it by a beneficiary.
Okay, so that could be. I already changed that, so we cannot ask that as homework as well. But maybe you could write the off-chain code for this as a homework. The students can write it as a homework. I think you should be able to do that.
Is it also possible in Icon to have more than one parameter, or does it always have to be one?
No, I believe you can have like as many as you
Okay.
want.
Right. Yeah. And in Lucid, I mean, you certainly can, because this apply parameter to script or whatever it was called took an array of parameters, right?
Yeah,
Right.
it was like.
I mean, you now use this vesting params type as one parameter. So alternatively, as yet another option, one could also use 2 parameters and the beneficiary and the deadline separate, right? As 2 different parameters.
Yes.
And that probably would not be exactly the same script, because the one is like a function with 1 argument and the other is a function with 2 arguments. Even though it behaves the same, it would probably be a different script.
Yes. Yeah. Yes, I think so. It's still like functional. I mean, it would have been more useful than putting them together, but the byte code, it will be different, I think.
Yes, I think so too.
Also, like for example, here I just added this new check, useless check. You can see if this is also like you can trace if this is the thing that fails, but you have to add some parentheses and then the question mark. So now you're going to see if this whole thing is true or false. But I'm going to remove it because I don't want people to get confused.
Right.
Yeah.
And then Icon would display the string G equals 5, or what? How would it?
Exactly.
Okay.
Exactly that. And because and of course you can, I mean, you can say like let check this specific thing equals to something, and then like this.
Uh-huh. I
So
see.
you get like a nice explanation in the
Right. Nice.
awesome.
Yeah,
So
good.
I think sorry.
No, I just want to ask what's coming on Monday. What's the plan for Monday?
So I think everyone should do the homework, because I do believe that you should be able with just these 2 lessons and all the code. I'm going to share all the code that we use until now. And then we can do minting.
Ah,
We
nice.
can, yes, I prepared like the 3 minting scenarios that we always prepare.
Uh-huh.
So that,
That is actually a lot of fun. So minting is about native tokens on Cardano, or maybe not native. Yeah, I think they are called native tokens, even if it's
Yeah.
not a native script. So, because I mean, most examples are much more fun when you have tokens, because I mean, then you can also have much more examples. I mean, like an atomic swap or something doesn't make much sense if all you have is ADA. But if you have different tokens, then it suddenly makes sense. And we can talk about NFTs and all these fun things. So yeah, that's really cool that on Cardano it's built in that you can create your own tokens. So that's what we talk about on Monday over Tino. But we only talk about Plutus minting, right? Or do we do native scripts as well?
I was going to only do Bluetooth minting.
That's fine, I suppose. Maybe you can mention it.
Yeah, maybe we could prepare something quickly, like for an example, or maybe explain the difference. But because we already are in Bluetooth, maybe native scripts are not that interested anymore. We can
Right.
do more. But yeah, next lesson you will learn how to create your own viral NFTs and tokens, so you can become rich.
Yes, mint your own NFTs.
Okay, guys. So thank you everyone for coming, and we'll see you on Monday. Any questions? Remember, we will answer them on Telegram or whatever you can ask them.
Thank you very much, Robertino. Thank you, Karina and Antonio. Very nice.
Thank you.
Thank you. Bye.
Bye. Have
Bye.
a nice weekend, everyone. Bye.
Nice week.
Thank you.